Okay, good afternoon and welcome to seminar series. I'd like to begin by again thanking the Cornell Atkinson Center for Sustainability for helping sponsor this seminar series. And today we're very fortunate to have Friederike Otto here and she'll speak to us on angry weather, identifying to what extent climate change is taking its toll. Freddie's Associate Director of the Environmental Change Institute at the University of Oxford and Associate Professor in the Global Climate Science program. So I'd especially like to thank Freddie for being willing to spend some of her evening here talking to us. And it's a real advantage of Zoom now. It's easier to bring in international experts into the seminar series, so they'll often have to talk to us from after dinner. So Freddie's research interest is on extreme weather events such as droughts, heat waves, storms, and understanding whether and to what extent these are made more or less likely or intense due to climate change. She leads several projects understanding the impacts of man-made climate change on natural and social systems, with particular emphasis on Africa and India. Freddie is a co-lead of the World Weather Attribution and international effort to analyze and communicate the possible extent of climate change and extreme weather events, which is hosted at the Environmental Change Institute at Oxford. And this has helped to change the global conversation around climate change, influencing adaptation strategies and paving the way for new sustainability litigation. 2019, Freddie was named one of New Scientists' Ones to Watch. In 2020, climate change attribution was named one of MIT Tech Review's top 10 breakthrough technologies. In 2020, Freddie became one of 10 international climate scientists who joined the co-writing team on the 6th assessment IPCC report, which I understand is taking a lot of her time. So we especially thank her for being able to spare some time to come speak with us today. So thank you, Freddie, and take it away.
Thank you. Thank you very much. Yeah, I'm still a bit puzzled why this science has been called one of the top 10 breakthrough technologies, because it actually doesn't involve that much technology, or it's not really a technology, but it's really more a method of just looking at the same kind of observational data and climate models that climate scientists used to look at before, but really just looking at it in a different way and asking slightly different questions. And so, yeah, what I'm going to speak about now for about 40 minutes, I think, is the basic ideas behind this kind of science that is called extreme event attribution. And then hopefully you'll have lots of questions, and yeah, I can answer some of them for the last half an hour of the seminar. So nowadays, whenever an extreme event happens, the question that the media, but also just the general public, politicians, everyone asks is, was this climate change? And until not so long ago, there were basically two answers that scientists would give to this question. The first one is that you can't attribute an individual weather event to man-made climate change. And the second answer was that, well, we are living in a world where climate change is happening. So every weather event is happening in a changed climate. And so, of course, it's influenced by climate change. And the latter is trivially true, but it doesn't actually give you any information about what this influence is. And the first answer is not true in this way anymore. So now we can attribute individual weather events to climate change, and we can also answer how much climate change has influenced weather events that happen in a changed climate. But of course, it is still true that every extreme weather event is ultimately, if you absolutely boil down to the individual event, is unique. And so it has every weather event always has multiple causes. There is always a role just of the natural chaotic variability of the weather system. There are always influences from just, was it a wet spring or a dry spring after which a heat wave might have occurred? Or is the weather event occurring over a city, over a forest, have large scale land use changes like deforestation or so occurred? All these things play a role in how the weather event ultimately plays out. And also human-induced climate change can influence a weather event, but it will almost never be the case that you can answer the question, was this climate change, with yes or no. The kind of question that you can answer is whether and to what extent man-made climate change has altered the likelihood and intensity of an extreme weather event to occur. And so the basic idea of how we answer these questions is very straightforward. When you observe a weather event, you observe always just one possible realization of all the types of weather events that are possible in this part of the season that you're interested in the climate we live in today. And when you look at the past records of observed weather events, you have a lot of data points of realizations of possible weather events in the world that we live in today and in the climate that will in the framework that is given from the climate system to these weather events. So, and this frame in which possible weather events that determines what are possible weather events are on the one hand given through just the incoming solar radiation, which is the main source of energy, then the distance between the Earth and the Sun, so the seasons, then how many greenhouse gases are in the atmosphere, and then other things like, for example, if there was a volcanic eruption that would have that has a big volcanic eruption with lots of ash particles in the stratosphere that blocks off some of the incoming solar radiation. So all these so-called external drivers determine what is possible weather that can occur. And the observed event is one realization of this. And so if we want to know what is possible, the influence of climate change, we have to do two things. First, we need to find out what kind of event is the extreme event that has caused impacts and that we are interested in compared to all the possible events in the world we live in today with climate change, with additional greenhouse gases in the atmosphere as we experience today. And then to compare that with a world that, a counterfactual world, a world that might have been without these additional greenhouse gases in the atmosphere. So a world that is exactly the same as the world we live in, but without climate change. And then also look at what is possible weather in that world. And so if you look at this schematic, what we do to find out is we look at observations, identify, okay, the extreme event we are interested in is extreme rainfall event following at the coast of Louisiana in September, and we want to know what kind of event is that in the world we live in today. Is it 1 in 100-year event? Is it 1 in 10-year event? And to do that, we can look at past observations of extreme rainfall events, but that also that doesn't give us all the possible events in the world we live in today. It just gives us a snapshot of realizations of possible events. And so we then have to use climate models and simulate what are possible extreme rainfall events in the world we live in today in September in the coast of Louisiana. And then in this totally exaggerated schematic that you can see here on the screen, you might then you get a probability distribution of your climate variable of interest, which in this case is extreme rainfall, and you define everything above a certain threshold that, for example, leads to flooding as your extreme event. And you might find that in the world we live in today, this extreme event is a 1 in 20-year event. And then we have to do exactly the same thing, but in the world that might have been without man-made climate change. And because we know very well how many greenhouse gases have been emitted since the beginning of the Industrial Revolution, we can remove these greenhouse gases in the atmosphere of the climate models, and so simulate the counterfactual world, the world that might have been without man-made climate change. And in this schematic here, you might then get a very different probability distribution of possible extreme rainfall events in September at the coast of Louisiana. And because you know that the only thing between these worlds that is different are the additional greenhouse gases in the atmosphere, you can then attribute the difference in the likelihood of the occurrence of your event to man-made climate change. So this is what MIT has called a technology, which is really not a technology. It's really just a different, an approach to use climate models and observational data and to create these two different worlds, the factual world we live in and the actual world, and simulate in both worlds possible weather. And if the distribution of possible weather is different, you then attribute this difference to man-made climate change. So with this is this schematic. Usually these distributions look much more similar than in this schematic. This is really just to explain the idea. But in some cases, you also find that these two distributions are very different. So this is an example of a study that we have done very recently. It's just been accepted for publication, but we published the results when we did the study in the middle of last year on the heat wave in Siberia in 2020, which amongst other things led to extreme temperatures above 38 degrees Celsius in Brasiliansk, which is extremely hot for the polar cycle, and found that in this case, the event would have been almost impossible to occur in the world without climate change. So it would have been a 1 in 80 million years event without climate change. And while still a rare event in today's climate, it is now an event that can occur. And so this is an example where climate change really, where you could say that this is one of the very few examples where you could say that, well, without climate change, this would really not have happened. But another example where climate change did play a big role is Hurricane Harvey that hit Texas or Houston in 2017, and where we found that the rainfall associated with Hurricane Harvey has been made 3 times more likely because of man-made climate change. And of course, you can then also use these kind of studies not just to look at the meteorological event, but also we usually are interested in extreme events because they have extreme impacts and because they lead to losses and damages. And Harvey had huge damages, also financial, economic damages. And so a colleague of mine from New Zealand used these attribution studies from the rainfall event and looked at how much of the costs of the rainfall you can attribute to man-made climate change, and found that of the $90 billion associated with the rainfall damage, you can attribute almost $67 billion to man-made climate change. But these are 2 examples where climate change really played an important role. But not all extreme events are being made more likely because of climate change. So another example that we have not looked at this year, but that became very relevant again this year, were cold waves in the UK. And you will all have heard of the cold wave in Texas. And there has also been a cold wave in North America in 2016. And together with colleagues, we've done a study on cold waves in all of the northern hemisphere. And you see what you see on this slide, all the red dots here are all the weather stations where climate change decreases the likelihood of extreme cold waves. And you can see that there are only very few stations where there is an increase in cold waves, and in the vast majority we see a strong decrease in the likelihood of cold waves to occur. And so that also means that if this cold wave in Texas would have occurred without climate change, it would have been even colder. Another example where climate change did not play a role was a drought we looked at in Brazil in 2014, 2015, that led to large water shortages. And there we did a study together with colleagues from INPE in Sao Paulo and found that this event, that was about a 1 in 10 year event in the world we live in today with climate change, was also about a 1 in 10 year event in a world without climate change. And actually looking at the observed records found that the same kind of drought from a weather perspective happened in the early 2000s and also in the 1970s with much smaller impacts. And then we looked at, okay, what else did change? And found that the population in the area around Sao Paulo, with the area of the drought, did increase quite a lot during the 10 years between this drought we looked at and the last drought. But in particular, the water usage increased almost exponentially. And so therefore a drought that had manageable impacts in the early 2000s, the same kind of drought had really devastating impacts because of the increase in vulnerability and exposure, not because of the increase in the hazard. So these are all typical results of attribution studies that you can find. And it's important to highlight that not every extreme weather event gets worse because of climate change. And the reason for that is that there are basically two ways of how climate change affects weather. One is what I would call the thermodynamic effect, and that is because we have more greenhouse gases in the atmosphere overall gets warmer. So on a global average, you have an increased likelihood in heat waves, a decreased likelihood in cold waves. A warmer atmosphere can also hold more water vapor that needs to get out of the atmosphere as rainfall. So on a global average, you also expect more extreme rainfall. But at the same time, because of the changed composition of the atmosphere, that affects the atmospheric circulation. So where weather systems develop, how they move. And this effect can be in the same direction as the warming effect. So it can be that, well, you expect more extreme rainfall because of the warming, and you also get more low pressure systems bringing that are conducive to rainfall. So you get even more extreme rain. But these two effects can also work in opposing directions. So if you can expect as much extreme rainfall if you like, if you just get fewer rainfall systems, it will not rain, or it will rain less. And so these two effects can either counteract each other, or if you want, the dynamics can win and you actually see a drying. And because the second effect is very different from season to season and from place to place in the world, you can't say without having done at least some studies in the area what the effect of climate change on a particular extreme event is. This is why we need to do these kind of studies. So this is the very basic overview. I'll now spotlight some of the more scientific aspects or caveats or scientific difficulties in these research, because in theory this is very straightforward. Doing it in practice is often not quite so straightforward. So this is how the plot with the two probability distributions I've shown earlier usually looks like when you do it for a real event. And you will realize that this doesn't quite look like your usual probability distribution. It's it's a return time plot, which you will be very familiar with if you're a hydrologist, not so much if you're not, but it's basically the very same thing as the probability distributions, but plotted in a way that you highlight what's happening in the tails of the distribution where the extreme events happen. So what you see here on the y-axis is the magnitude or intensity of the event of the climatic variable. And so in this case, this is an extreme rainfall event associated with Storm Desmond that led to large-scale flooding in the UK in 2015. So you have here rainfall in millimeters per day on the y-axis, and on the x-axis is the return time on logarithmic scale. And this red curve here, which is red dots with red bars across it, every red dot is a simulation of a possible rainfall event in December 2015 in the UK, in the world we live in today. And so in the world we live in today, every 10 years, we expect a rainfall event of 10 millimeters or a bit, maybe 11 millimeters a day or more. And every 100 years, we expect in the world we live in today to see a rainfall event that is 17 millimeters or higher per day. So this is how you read this this graph. And all the blue dots are simulations of exactly the same thing. Possible rainfall in the UK in December 2015, but in a December 2015 as it might have been without man-made climate change. And you can see that these two curves are different, but only slightly so. So what in the world that might have been used to be a 1 in 100 year event is now in the world, is now in the world. So if you look at the 1 in 100 year event here in the world that might have been, is now in the world we live in today, maybe a 1 in 70 year event. And so you still have this type of event is still a once in a lifetime event, but it has significantly become more likely because of man-made climate change. And you can also see that while for the less rare events, these curves are relatively quite distinct, and these vertical bars, horizontal bars, are relatively short. They become very long for the very rare events, and this is because they represent the uncertainty from the from the sampling of the event. So if you have 100 simulations, you can't really say much about the 100-year event because you would only have one realization of that, but you could say a lot about the 1 and 5-year event. And similarly, if you have about 1,000 simulations, which is sort of what we have here, you can say something about the 1 and 100-year event, but it becomes quite, the uncertainty becomes quite large already for the 1 and 500-year event. So this is more the kind of result that you see for a real event that is not a big heat wave. And these kind of studies have now been done a lot all over the world. And of course, what you see on this plot here is one model which has the sampling uncertainty. But of course, that's not the only uncertainty that you have coming into these kind of questions from what we know about the real world, what we can model and what we can measure. Another very important point is what has actually happened in the real world, because before I do this study and know what I want to model, I need to know what is it actually that has happened in the real world and that has caused the impacts to occur. So, for example, when we, with our World Weather Attribution team, do an attribution study, we always work with the Red Cross, and they usually ask us, here is some bad event happening with lots of impacts, can you do an attribution study? And they don't tell us that the kind of information you get about an extreme event happening is usually not, oh, it has been raining in this particular area above 100 millimeter per day. Instead, you hear reports there's large scale flooding in this example in central Kenya. Can you say what the role of climate change is? And so the first thing you have to do is to find out, well, what actually caused these impacts? Was it a one-day extreme event that led to flooding in the area? Or was it that it was a very soggy season that then led so that the whole rainy season was exceptionally wet, and so that led to flooding? Or did it actually rain a lot somewhere else further upstream, and because of some river management or just the natural hydrology, it flooded in the area where it flooded? And so in order to answer these questions, you need observational data. And observational data is still extremely difficult to come by for most variables and for most parts of the world. And so this is an example of a rainfall event in Kenya on the 10th of November in 2 different observational data products that are publicly available. And you see on the left one, you have here a very strong rainfall event, which has over, in its center has almost 50 millimeters per day of rainfall, which is a lot. So if you, it rains about 700 millimeters a year in the UK. So 50 millimeters a day is extreme amounts of rainfall. But if you look at a different product from the same day, you hardly see, you see some rainfall events in slightly adjacent parts of the country, but not actually even in the same part. And so the question is, well, if we want to do an attribution study, how much did it rain, when, and where? And so these questions are very difficult to answer in many cases, and you always need you need to always work with people who actually know the local meteorology and have ideally access to not just satellite data or global data products, but to weather station data. And there is, and there's then always also a trade-off between what actually happens and what you can measure and what you can know. This is a relatively extreme example, but it's one that's very easy to find. So there's always some mismatch in different observational data products, and it's not, sometimes it's easy to find out if there are obvious errors in a product, but not always. So the next question then, assuming you have now found, okay, this is a data product I can trust, and so therefore we assume we know how much it rained and where, then the next thing is, well, of course, you can't just use observations because observations are very limited. So you only have the observed realization of possible weather. And also, of course, you will have a hard time to simulate the world that might have been without climate change by just using observations. So we do need to use climate models as well. And climate models all are good for something and really bad for other things. And so this figure is really just as an illustration, so it's not terribly important what is on the figure. But if, for example, you're interested in a heat wave in Europe, then you could look at the maximum temperatures in the observations, and then you might use just that to define the heat wave that you're interested in. But you might also say, well, some heat waves in Europe are because of a large high pressure system over Scandinavia, and other heat waves in Europe are because of extremely warm air coming in from the Mediterranean region. These are different, so maybe I just want to focus on one of these types of heat waves, and then do the climate models that we have available and represent the right kind of temperatures in the first place, and then do they actually simulate the different weather systems that are responsible for the heat waves in a reliable way. And climate models are not perfect, so there is always a trade-off between what climate models can reliably simulate and what has actually caused the impacts. And the difficult thing is to find, okay, what is the right way to define your event, that you have important information that is related to what people are vulnerable to, but is also something that the climate models, the state-of-the-art models, are actually able to tell us something about. And so once you have done all this, the results you get from these kind of attribution studies look more something like this. And what you can see here, so just focusing on this left-hand side, a heat wave in Germany in 2019. We have on the one end the observations, and we can look at how just in the observed record, which is relatively long in Germany for heat extremes, so over 100 years. So you actually have also quite some representation of past climates in that. And by using statistical modeling on these observations, you can use that as one way to simulate the world we live in and the world that might have been. And you find, based on this, that this type of heat wave that has hit Germany in 2019 was made about, if I can now read my logarithmic plot, about 300 times more likely because of climate change, but also the uncertainty around this is very large because there's only so much observational data. And then we have used many different climate models to ask exactly the same question, simulate possible heat waves 2019, possible heat waves in a world that might have been. And you find that in these different models, you find about a 10 times increase. Here in this particular model, you have slightly larger increase of about 80 or 90 times. This one has a slightly lower one, but all the models have quite a strong, a very systematically lower increase in the likelihood of this event to occur than you find from the observations. And of course, observations also contain other things than climate change that have changed, land use changes, for example. But these can't, in this case, really not explain this big difference. So there's obviously something systematically wrong with these climate models. If I had used a heat wave example for the US, you likely would find the exact opposite, that the models all have a stronger increase than the observations. And so the only thing that we can really say in this case is that climate change made this event at least 10 times more likely. But we can't say if it's 100 times or 1,000 times, because we just don't have the right tools for this very localized heat wave to answer that question. A better case is the extreme, sorry, I shouldn't click on my slides, is the extreme rainfall event in Texas that we have also looked at. There you see that in two different observational products, you have about a 2.5 times increase in the likelihood of the event. And in the two models that are good at simulating this type of event, you also see about a doubling of this event in one model and a bit less than that in the other model, but it's still very much the same order of magnitude, very close. So there you have a much more constrained result that you can give for your for your event attribution study. And the last example here, which is the drought in Somalia in 2010, you have basically that in the models, on the one model shows an increase in the likelihood of drought, the other one a decrease in the likelihood of drought. And also your observations show a small increase, but the uncertainty around it is so large that the only result you can give is that you can exclude that climate change was a complete game changer in this case. But with the current tools and understanding and observational data, you can't give more than that as a result from your attribution study. And so to summarize, there are always 4 possible outcomes of an attribution study. The event can have been made more likely because of climate change. It could have been made less likely. It could be that climate change did not really alter the frequency or intensity of the event. And also that with our current understanding and tools, we can't assess that because we don't have good enough observational data. Our models are not good enough, so we don't know. And these kind of studies have been, the first study has been done in 2004, and then a couple of studies have been done a few years later in 2012. And since then, every year, more and more studies have been made. And so on this map that has been put together from Carbon Brief, which is a UK news and climate, energy and news outlet, you see in red are all the attribution studies which found that climate change played a significant role. The blue ones are the ones where climate change did not play a role, and the gray ones are the ones which were basically inconclusive because the current models or observations are not good enough to answer the question. It's very important, though, to highlight that this is not representative of all the events that are happening. And because it's very hard to publish a study that's inconclusive, that has no real result. So a lot of the studies that would be gray will never be published, so will never appear up on here. And also, you can even see that there are lots of studies in the US, a lot of studies in Europe, and it's getting much thinner here in South America or Africa. And on this map, I have tried to find out how big this discrepancy is between what extreme events are happening that have large impacts and the types of extreme events where we know what the role of climate change is. And so what you see on this map is in red are deaths associated with extreme weather events per country. So these circles are on the capitals of the country, and the larger the circle, the more death associated with extreme events. And in black are the circles within the red circles are those death associated with extreme events for which we know the role of climate change. It doesn't mean that all the black ones are because of climate change. It's just that all the black ones are where we know whether and to what extent climate change played a role. And you can see very strongly here that this, for example, in Russia, that was a big heat. The largest death associated with extreme events was a heat wave in 2010, for which there have been quite a few attribution studies. But here in Myanmar, the most extreme events, the most deaths have been associated with a tropical cyclone, for which no studies exist, and also for the other events in that country, no studies exist. So you see that there's a very strong discrepancy between what we know about extreme events in the developed world and in the developing world. And on the one hand, this is because of data availability, but to a very large degree, it's just who is doing the science and where scientists are sitting. And also, what is important to highlight here is that we might I have used death here to indicate extreme events, not because I'm particularly morbid, but because it's an impact of extreme events that is relatively good comparable between countries. If instead you would use economic impacts, for example, you normally only have them for insured economic damages. And so you have in many developing countries, you don't have much insurance. So the economic costs would be quite low, but not really represent how bad the event was. So that's why I've used death, but you could use other indicators as well. But what is also important here is that these might not really be capturing all the extreme events that are happening and that cause death. For example, if you look at this map, which is from a global database called EMDAT that associates, that just counts disasters. So disasters from volcanic eruptions or earthquakes, but also disasters following extreme events. And so this map is for heat waves. And here also, the larger the circle, the more heat waves have occurred. And you can see that in most of Africa, there is no data. So there is no record of any heat wave impacts or any heat that have occurred since. So this map is from 1985, but we have in the paper that is referred to here, we have looked from 1900 onwards, and the map does not look any different. But when we look at observational data of temperature, we see that there are a lot of heat waves, and heat waves are increasing also and particularly in Africa. So this is one big heat wave in Southern Africa that probably led to quite a lot of death in the early 90s. But these are not reported because, and there are reasons for that. So in many developed countries, governments actually report impacts of extreme events and they get feed into this database. But in many developing countries, it's NGOs or the Red Cross who do the reporting of impacts of extreme events. And impacts from heat waves are very difficult to account because you would need to go to the hospitals and find out actually, was there additional mortality and what was the reason for this additional mortality? And that is something that only happens if governments request hospitals to do this. And so this is one of the main reasons why we have this discrepancy. But this also means that not only do we not know for many of the extreme events where we know that they have led to impacts, the role of climate change, but also there are a lot of extreme events happening that actually are not registered. And it's particularly heat waves for which climate change is a real game changer. And so I think I will actually end here now because I've talked enough and I would like to give you the opportunity to ask some questions. I had 2 more slides, but they are not so important. So yeah, I'll stop here.
Okay, thank you very much, Freddie. We have a number of questions in the Q&A, so I will go through some of them. So there's a question here from Sarah, and I guess she's asking is, have you noticed that any particular regions are more likely to show a causal effect between anthropogenic climate change and extreme weather events? So I guess she's asking, are there some regions that might be more affected than others, despite the more data in some regions than the other? For example, you look like you saw more in Europe than in the US, for example. Would you expect that, or
so I think, I think we see more in Europe and more in the US because these regions are studied more. So I think it's not that there are some regions that are more affected than others. It is definitely the case that some types of extremes are showing a much stronger climate change signal. So heat waves and cold waves are by far the types of extreme events where climate change really is a game changer and makes the events orders of magnitude more likely in the case of heat waves and less likely in the case of cold waves. But of course, there are also regional differences. So in Europe, the increase in heat waves is a lot stronger than in for example, in the US. One reason there is that in the US, you have a counteracting effect from large-scale irrigation, which leads to cooling, and so you don't have quite so strong an increase in heat waves than you would expect from, or than you have in other parts of the world from heat waves. But also in Eastern Africa, you see a very strong increase in heat waves, stronger than, and there's also a big role from just natural variability. And for other types of extreme events, we see quite some regional differences. So droughts, for example, there's an increase in drought in the Mediterranean and also in southern parts of Africa, but not really anywhere else in the world. And for extreme rainfall events, it's a bit more even across the world, but also there are some hotspots. Well, I know that Northern Europe is a particular hotspot, but also northern parts of the US see an increase, and also the Gulf of Mexico region. But I don't, there are also quite a lot of regions in Asia that see an increase in heavy rainfall, but I don't know that so well.
Thank you. Here's a question from Aiden. And the question is, how would you communicate the results of these attribution studies to climate skeptics? even climate deniers, or I might add also the media who wants to blame every event on climate change?
That's a good question, and I'm not sure if I have the perfect answer to that, because quite often one feels a bit squished between doom and denial. And I think climate change is bad enough as it is, even if not every bad thing and every extreme event that happens is due to climate change. And so, yeah, how would I communicate that? I think I always try to communicate not just the result and say, okay, this event was made 100 times more likely because of climate change, but to explain the process of how we got to these results. Of course, you can't do that in every news article, but over time, and I think we have actually managed to do that with the World Weather Attribution Program that we have, that we do a press release or a press briefing every time we do a study and invite journalists to ask us questions. And so we have an increasing basis of journalists who know and understand what we're doing and can report on it. This, of course, is not, this is not the perfect way to do it and takes quite a lot of time. But I think the other thing is just to use metaphors of what is happening. So a good metaphor is, for example, well, if you're a soccer player on steroids, not every goal that you score is because of the steroids, but you increase the likelihood of scoring a goal because you can just run faster than the others, and so that works as well.
Okay, thank you. Question from Benjamin. How could this technology be used to combat the climate crisis? Can it be used for postmortem analysis, or can you see a way that this could be used in which it would help prevent further damage? And I might add, can it be used to litigate, for example, or has it been used to litigate?
So that was the 2 slides I skipped.
Okay.
I can, but yeah, I actually don't need slides for that. So I think actually the most important thing that we can use, that this science is useful for, is to learn from past experience and to understand our vulnerabilities. Because at the moment, as I've tried to show, we really don't have an inventory of the impacts of climate change. In most cases, we don't know what the impacts of climate change in the US are. We don't know what the impacts of climate change in Europe are. We have some snapshots of some events where we know that climate change played a role. But if we would use, we actually now have all the tools available to build such an inventory. And if we would use the information that we have after every extreme event that has occurred of the damages and can look at the observational data and find out what aspect of the weather did actually cause these events. Was it the 1-day extreme rainfall event, which is something that climate scientists always look at in future projections? Or is it actually something else? Or is it the 1-day extreme temperature event? Or is it actually the combination of drought and heat that causes the largest damages? And from this, we can then use attribution from understanding what actually causes the damages. We can then use that kind of events to understand what the role of climate change up to now was, but crucially also how with future warming, these might change. And I think that is probably the most important thing that we can learn from these post-mortem analysis to make better and more relevant projections, and so to do adaptation. But of course, you can also use that to sue people, and that is happening. So one example is that's at the moment ongoing in in Germany is that a Peruvian farmer has sued RWE, which is the largest German carbon major company, for the emissions of that company, because it led to melting of the glacier in the vicinity of the city of Juarez, where that farmer is living, and that has led to a large increase of a glacial lake, which is now threatening the city with outburst floods. And so that farmer, they are suing RWE, so that RWE partakes in the adaptation costs that that occur to save Juarez from these floods, with the argument being that because RWE knew very well that their business model led to climate change, which leads to the glacier melt, so that they knew, and they are in part responsible for these causes. So that case is still pending, which is quite exciting, because while it has been dismissed from the lower court, it's now pending in the higher court. And at the moment, it's in the evidentiary stage, so that expert reviews experts are heard, whether you can actually make that causal link. And in that case, you can make that causal link very clearly, because basically the glacier would not have melted at all without climate change. So there are quite a lot of other climate litigation cases. The successful ones have usually been not based on particular attribution studies, but more like one successful one in the Netherlands, where the state of the Netherlands, the Dutch government, didn't do what they promised in their own NDCs. So that was a relatively easy case, because you actually didn't need any scientific evidence. You just needed to prove that they didn't do what they said they would do. A more closely related example is that in Colombia, the government of Colombia was sued by youth groups to stop deforestation in Colombia on account of future climate change that would occur because of the deforestation, and that was successful. But I think it's just a matter of time until more of these cases are successful, because it's really only now that the science and the law are starting to understand each other and speaking the same language, and so can bring the things that you can actually attribute to court, and in a language that actually a jury can do something with.
Interesting, thanks. Here's a question from Amy. She wanted to know what inspired you to create this new way of looking at the data and ask these questions about extreme weather. So how did your research start in this direction, I guess?
It actually it started with the Russian heat wave. So because after that occurred in 2010, and there were two papers that were published after that, one from a group in Germany that said this was climate change, and another from a group in the US that basically said this was not climate change. And I then said, well, this can't be right. And so I looked at these two studies and tried to figure out what they actually did, and found that they asked very different questions. So the one from that said it was climate change basically said, well, did climate change play a role in record-breaking temperatures? And yeah, of course, if you have a trend, then you break records. And the other one really actually asked the question, could you have known in June that there would be this big devastating heat wave in July and August because of climate change? And you couldn't really, because there were also a lot of other natural variability that played a role. And so that brought me to the question, well, there needs to be some some other way to answer that question. What was the role of climate change? That is a bit more, that actually is more related to what causes the impacts, and so a bit more relevant way of asking that question. And that was how I started to think about that. And then also the people I work with in Oxford at the time had already started to think about these methods. So it was also a lot of just being at the right place in at the right time.
Great, thanks. So a question from Emma. Can this type of modeling be used to attribute non-weather events such as species extinctions, crop failure, maybe forest fires in California to climate change?
Yes. So in principle, definitely. In practice, it's quite often tricky, but so you can, and we have done that with actually in some cases. You can, so you have the weather event that is related to the crop failure, for example. So the crop failure might be because of drought, and then you can use simulations of possible droughts from a climate model, drive a crop model, and see what the likelihood of that crop failure is with climate change, and then do the same thing with the counterfactual likelihood drought simulations, and then do exactly the same thing. And you can also, and we've just tried to do that or done that in the case of food insecurity in Lesotho, where we have simulated on the one hand the weather events, the drought, and there was 2 droughts, one drought in Lesotho and one in sort of in a slightly different part of Southern Africa, which basically was the part of the world where Lesotho imported their crop when they had the drought, and so they had a drought and they didn't have their crops from their homegrown crops, and they couldn't import it because there was a drought, a simultaneous drought in that. And so we basically had several counterfactuals. We had once just the drought in Lesotho, then the droughts in both cases, but then also a lot of other things, a lot of his impact, these trade dependencies and crop prices. And so we tried also to have a counterfactual of, okay, assuming that historically these interdependencies had developed in a different way, how could you take that out from the climate change effect? And then of course it gets relatively complicated, but in principle you can do this. You can just, if you can model it, you can also model the counterfactual, and so try really to disentangle different drivers of a disaster to find out which ones are the big problems. And then also, of course, that is also very relevant if you want to know, okay, is what had just happened, is that a harbinger of what's to come? Because climate change, we know, will continue, but other things might not, or might continue in a different way. So I think this is really where the really interesting questions lie, and where we need to get better and dig deeper and try to figure out how to do this properly.
Thanks. And a question from Siobhan, probably mispronouncing your name, sorry. Do you use, so this is going back to predictive modeling, do you use any predictive modeling where you attempt to predict the likelihood of an extreme event will change in the future? Climate change is not mitigated. So maybe the question is, to what extent is this emphasized in the IPCC, or looking at future extreme events and their impact?
So, well, exactly the same method that we use to do sort of the world today at 1.2 degrees and the counterfactual world without climate change, you can use that, okay, and what's possible whether in a 2-degree world, or say in a 4-degree world if we don't manage to mitigate and if things go bad. So yes, you can use exactly the same methods, and I think increasingly my team at least, and also others are starting to do this, assessing changes in extremes across timescales from the past to the present into the future, and looking at different futures. There are quite so a lot of the impact assessments are for sort of 4-degree worlds, and they are not really doing the same thing as we, for example, do with the attribution. So it's a bit difficult to compare these and to have exactly this seamless past, present, future. So there is still some more work to do, but it is done, and increasingly different lines of evidence are combined to also assess the uncertainties in there.
Great, thanks. And there's some number of questions about data availability. So one question here by Elena. What's the reason why developing countries don't report the damage caused by extreme climate events? And related by Manuel, are there efforts being made to provide more consistent data in places that have a lack of it?
So one reason for the data issues is that in many so you can make money with observational data. So not all countries publicize their data, but instead sell it to insurance companies or hedge funds or everyone who would like to have good observational data. And so they exist, but they don't exist for science purposes. And there is, and this is really not just a developing country issue. So, for example, try to get observed data out of Poland that's also very, very difficult. And so there, and also, so the US has been really good in that. So US data has been public for a long time. But for example, Germany has only started to make their data publicly available a couple of years ago. So there is some thinking that it actually benefits the countries if they publicize their data. And so that is just something that hopefully will filter through to the rest of the world as well. But then, of course, well, if the data isn't there, you can't invent historic data. But in many cases, it's also that the data is not digitized, but that it exists just on a piece of paper. And so there are campaigns and projects that digitize old data. And so that is a way that more data is becoming available. But I think it's really something that there is not always an understanding of how important this data is. And so that, well, also if you have, if it's not a priority of a government, then you just easily have just gaps in the data of, I don't know, the guy who works at the station retires, and then you have a gap of several years. So it's just something that is only starting to be seen as crucially important. So there will be gaps that can be filled, but there will also be gaps that will just continue to be there.
Yeah, okay. Thanks. And questions from Nathan about the wildfires in California and Australia. Have there been studies yet looking at these events, and have they been attributed in some way to climate change or not?
So we've done with my team, we've done a study on the bushfires in Australia, and found that climate change made them at least 30% more likely. And that increase in likelihood is primarily due to the increase in temperature extremes, because, well, we looked at fire weather, so the meteorological component, so extreme temperatures, wind speeds, dryness, and it was basically that this signal is coming through the temperatures. We have not looked at how much. So we have really looked at the meteorological fire weather component. Of course, there is an important role of whether there's fuel available, how the forests are managed, which is we haven't done a study on the California wildfires. I've had many conversations with a scientist from California who works on forest management and who looked at management practices, how they have changed, and that sort of regular deliberate burning has stopped, and so there was a lot more fuel available, so that in the California case that these things will play a role, but also well, I don't know, I can't quantify the climate change component in California because we haven't looked at that, but extreme temperatures are also going up in California and have gone up, so everything else being equal, there will also be a climate change signal in that.
Great, thanks. And probably have time for one more. A question here from Jack about counterfactual simulations. Are they based on just running climate models? See, I lost my question here. See if I can find it. I think I guess the question is with and without greenhouse gases, or do you include other aspects of global change in the simulations, maybe land use or something else?
It depends on what question we ask. So the most easily available simulations are the ones where man-made greenhouse gases and man-made aerosols are removed from the atmosphere. So you have the atmospheric component of climate change, which is what you attribute. You can also just do greenhouse gases or just do aerosols. And there are a few studies, not many, but it's absolutely doable, where land cover changes or land use changes have been removed. So again, if you can model the component you're interested in reasonably well, you can also do a counterfactual. But the most common one is to remove the greenhouse gases and aerosols.
Great. So thank you so much. I think we're out of time, and very much appreciate you coming and talking to us. It's been a great seminar, very educational. And yeah, good luck with the new IPCC.
Thank you. Thank you very much. Yeah, I hope it was useful, and sorry for not being able to answer all the questions. But I hope, yeah, some answers can be still found.
Great. Okay. Thank you. Have a good evening. Bye-bye.
Thank you. Bye.